All right, so just to reiterate, from the previous page, we were looking at the average and instantaneous velocity. And average velocity, since average means like over an interval, we can calculate that value by using the slope of a secant line between 2 points, meaning the beginning and ending point of that interval. Whereas instantaneous velocity is represented by the rate of change at 1 point. So that would be indicative of a tangent line on the position graph, aka a derivative value. So moving on to another characteristic of particle motion, we have position so far, which is just representing the location of the object. Velocity is representing the speed and direction of the object, how it's traveling. And then we can talk about acceleration. And just like velocity, we can have two different types. We can have average acceleration, meaning over an interval, or we can have instantaneous acceleration, meaning at 1 point in time. So if we have these two different types, average and instantaneous, that is representing the rate of change of something. The question is, what is that something? So if you think about acceleration, if you're going very quickly or very slowly, or I guess that would be more of a velocity terminology or description, but acceleration is basically how quickly your speed is changing. So using a driving example, if you press down on the gas very forcefully, obviously your speed is going to go up very quickly. So the rate of change can be found by doing either the average or instantaneous calculations from velocity. Okay, average rate of change of velocity. So if we want to do an average, this would be the slope of the secant line, meaning 2 points, on the velocity graph or velocity function, okay, or velocity table, whatever is given to you. So the slope of the secant line on velocity. Instantaneous would be the slope of the tangent line, aka 1 point, on velocity. Basically meaning it's the derivative of velocity. Now, this kind of brings something into consideration here. If we're finding the derivative of velocity, and if velocity in itself is a derivative, okay, velocity is the derivative of position, then technically this instantaneous acceleration is the derivative of a derivative, which is signifying a second derivative. So we could also give a definition or a description for instantaneous velocity. This is the second derivative of position. Meaning if you start with a position function and you take a derivative 2 times, that equation would represent your instantaneous acceleration. Okay, so instantaneous acceleration technically has 2 definitions. It could be the derivative of velocity or the second derivative of position, whatever information you have available to you. So let's take a look at an example. A particle motion is given by this function. This actually happens to be the same function we had on the previous example. Same units, centimeters and seconds. What is the average acceleration on this interval? So average acceleration is the slope of the secant line on velocity. But notice how the function they give us is position. So we have to think about how is velocity related to position, and velocity happens to be the derivative of position. So even though this is position, we can take the derivative of it, which I believe we already did on the previous page using our product rule. So we'll just go ahead and write that down again. All right, so here's our velocity function. Now if we're going to calculate average acceleration, we need the slope of the secant line between 1 and 3 on this graph or this equation. So let's calculate v of 1, and we'll calculate v of 3, and then find the slope between those 2 points. All right, 3.75605. Again, this is not our final answer, so we should most likely go out further than 4 decimal places. negative 17.05006. All right, so average acceleration is equal to the slope between these 2 points from our velocity function. So we'll do change in y's over, I missed a number there, over change in respective x's. Negative 10.4031, okay, or you can do 0, I guess, if you chop it after 4, but I'm going to go ahead and round it to 1 spot. All right, so this brings into kind of something new for us is the units. And again, if you've taken physics before, you might be familiar with the units of acceleration, but if you haven't, we really got to think about what these numbers represented. So if this negative 17 and 3.7 number came from velocity, the units on these numbers we said were centimeters per second. Now these numbers down here are second values. So we really have centimeters per second divided by seconds. So using some little algebra here, centimeters per second divided by seconds, instead of dividing by seconds, you could technically bring it up and multiply by the reciprocal, which would be 1 over seconds. So this would eventually lead us to centimeters up top, and then seconds squared on the bottom. So an acceleration unit is always going to have a squared time value, or not value, a squared time unit on the bottom. And a nice way to kind of help this sink in, or maybe you can find some connections here, is since acceleration is technically the second derivative of position, this power of 2 is kind of signifying that connection or that relationship. So we essentially took a derivative, aka a simple rate, and when we divide it again by those x units, we're taking another derivative. We're doing another rate of change. So that's going to bring in an additional unit that we have to use when we write them. So that's going to be our power of 2. All right, so moving on to instantaneous acceleration. This is the derivative of velocity, aka the second derivative of position. So if we were to take the derivative of our velocity equation, which we have up here, now we have 2 terms here, and both of them are being multiplied separately, so it seems like we're going to have to do the product rule twice. If we do product rule on this first term, we'll have 1 d2 plus 2 d1, all right, and then we're going to have to add the derivative of these, or that second term. So we'll have 1 d2 plus 2 d1. All right, looks good. Now, if we look at it, you can keep this as v prime, but technically the derivative of velocity is acceleration. So if you want to change the function notation, that's completely okay. So you actually know what this represents. You can say that this is the acceleration function. If we take a look at what we have here, notice how this negative sign e to the t and this positive sign e to the t, those will technically cancel, and then these two are the same exact terms, so if we add them, we'll have 2. All right, so there's our simplified acceleration function, okay, the acceleration or instantaneous rate of change at 1 point. So if we go ahead and plug in 1.5, we'll see what we get. And I got 0.634. If we go to 4 decimal places, it looks like we have to chop it at 0 because the 4 would not round it up. There we go. And since it's our acceleration, we're going to have centimeters per second squared. Okay, acceleration is a second derivative, so we're going to have that squared unit on the bottom. So at this point in time, 1.5 seconds, this is how fast the speed is changing. Since it's positive, the speed is changing quickly. Okay, it is accelerating at some value.